Hi everyone, I appreciate this great opportunity to talk about this topic. So currently I'm working in recycling chemistry laboratory in Tohoku University. So in this laboratory, I'm researching development of feedstock recycling technologies for waste plastics and biomass, so which includes pyrolysis, co-pyrolysis, and catalytic pyrolysis approaches. In addition, I also belong to Innovative Analytical Pyrolysis Laboratory, so which is an endowed laboratory established by Frontier Laboratories. So as you know, Frontier Laboratories has developed analytical pyrolysis instruments and methods, and has manufactured microfurnace pyrolyzers. So in this laboratory, I'm working on development of new analytical pyrolysis techniques using microfurnace pyrolyzer gas chromatograph systems. So today I want to talk about combined UV irradiation and PYGCMS approach for evaluating deterioration behavior of ethylene vinyl acetate encapsulant for PV modules. So this is general outline of today's talk. So firstly, let me start from the brief introduction of pyrolysis gas chromatography. Then I'll move on to today's main topic about UV deterioration behavior of ethylene vinyl acetate. And finally, I'll summarize today's talk. So let me start talking about pyrolysis and pyrolysis gas chromatography. So pyrolysis involves the decomposition of polymeric materials which have low solubility, high molecular mass, and low volatility. So pyrolysis of polymeric materials produces smaller molecules by the application of heat alone in an inert atmosphere. So in the case of lignocellulosic biomass, pyrolysis of it produces gases such as carbon monoxide, carbon dioxide, methane, and etc., and liquids such as anhydrous sugars, frans, oxygen-containing C2C3 compounds from cellulose and hemicellulose, and methoxyphenols with wide variety of side chains from lignin. Most of the pyrolysis research are roughly categorized into applied pyrolysis and analytical pyrolysis. So applied pyrolysis involves the development of pyrolytic processes for producing variable chemicals, energy carriers, and materials from fossils, renewable feedstock, or waste, along with the recycling of materials and the disposal of toxic substances. So on the other hand, analytical pyrolysis enables elucidation of chemical composition and structure of materials in the wide fields, involving the use of new instrumentation and new analytical methods based on pyrolysis reactions. So I guess that many of you in this symposium are working in the analytical pyrolysis field. Pyrolysis gas chromatography allows pyrolysis of polymeric materials in a micropyrolyzer, followed by GC analysis of the pyrolysates. The necessary sample amount is micrograms to milligrams. Capillary columns and mass spectrometer have been commonly employed for PYGC, so whereas the detection system should be selected to suit the purpose of pyrolysate analysis. So this image shows a microfurnace type PYGCMS system. So you can directly put solid or liquid sample in the sample cup. So if you want to conduct pyrolysis with a slow heating rate, the sample holder should be set in the furnace and is gradually heated up, like thermogravimetric analysis. On the other hand, if we want to try fast pyrolysis conditions, the sample cup is located at the upper part of the furnace, so where is the outside of the furnace until the furnace temperature reaches to the desired temperature. So when the furnace temperature reaches to the desired temperature, the sample cup is dropped into the furnace. Thus, microfurnace type PYGC allows both rapid and slow heating and broad temperatures. The pyrolysis products are directly introduced into GC column, so we can skip the process of pyrolysis products collection. So pyrolysis gas chromatography can be applied to wider areas of analytical targets than other analytical techniques, including gases, liquids, solids, together with cross-linked polymeric materials, which is solvent insoluble. So this feature is vastly different from other analytical techniques such as liquid chromatography and gas chromatography. So as many of you might know, Pyrolysis-GC is available for identification of pyrolysates by employing a separation column, so which is called PYGCMS method. Also, when you set lower temperatures than polymer degradation, organic additives in the polymer can be analyzed by GCMS without influence of polymer pyrolysates, so which is called thermal desorption GCMS method. So when you employ a deactivated column, so you can conduct in situ monitoring of the evolved gas. So these are conventional ways of use of pyrolyzer GCMS. So today, I introduce a combined UV irradiation and PYGCMS approach for evaluating deterioration behavior of EVA encapsulant for PV modules. So let me start from why I'm researching EVA deterioration. So as many of you know, the current global PV market is huge, and the total installed capacity reached 500 gigawatt in 2018. So PV modules typically come with 20-year warranties. Therefore, after 20 years from the installation, used and waste PV modules generation will be significantly increased. So therefore, predicting generation trend of used PV and PV lifetime is important for management of reuse and recycling of PV modules. The deterioration of the ethylene vinyl acetate EVA encapsulant under prolonged exposure to sunlight causes its discoloration, delamination, and corrosion, so which are known to be the principal causes of loss in power generation. So these phenomena are commonly observed in PV modules used for 20 to 30 years. So these are generally detected by visual and electroluminescence inspections, whereas the reduced transparency and short circuit current are evaluated by transmittance and IV curve measurements, respectively. So my current work is the investigation of the deterioration behavior of EVA encapsulant during UV irradiation. So understanding UV deterioration mechanism is important to evaluate or predict the deterioration level of EVA encapsulant. Okay, so firstly, samples of 2 mm diameter were collected from the commercial encapsulant seed for PV modules using a micropuncher. The 18 films of 2 mm diameter were placed in the multi-sample micro-UV irradiator developed by Frontier Laboratories. The samples underwent UV accelerated deterioration at 60 degrees for the maximum 672 hours. The PV source has a wave number from 280 to 450 nanometer with the maximum intensity of 500 watt per square meter. The deteriorated EVA encapsulant was characterized by various methods. Okay, so digital microscope and SEM images of the EVA encapsulant are shown here. So following the UV deterioration of the EVA encapsulant at 60 degrees for 168 hours, discoloration was observed. The SEM images of the UV deteriorated EVA encapsulant showed cracks and bubbles, suggesting the formation of gaseous products during the UV irradiation. The oxygen content of the UV deteriorated samples prepared at different UV irradiation intensity reveals that the oxygen content is increased with aging duration. The absorbance attributed to CO stretching at 1,615 Kaiser derived from aliphatic ketones in the EVA encapsulant increased with the duration of UV irradiation. In addition, the gradual enlargement of the broad bands in the vicinity of 1780 Kaiser with increasing UV irradiation duration, so which was not observed in the fresh samples, is attributed to the CO stretching of lactone, providing evidence for the formation of these compounds. The absorbance attributed to ketonic CO stretching at 1715 Kaiser increased further under the UV irradiation than that of lactone, suggesting the preferential formation of ketones. Furthermore, the UV-deteriorated EVA encapsulants were analyzed by EGA-MS and PYGC-MS methods to predict the structure of the aged EVA encapsulant from the pyrolysis characteristics. For EGA-MS analysis, the fresh and aged EVA encapsulants were decomposed by heating from 50 to 900 degrees at a rate of 10 degrees per minute. An ultra-alloy deactivated metal capillary tube UADTM column was employed and helium was used as the carrier gas. The pyrolysates were introduced directly into the MS. The GC oven temperature was set at 300 degrees Celsius. For PYGC-MS analysis, the fresh and aged EVA encapsulants were pyrolyzed in the reactor furnace at 370 degrees Celsius for 40 minutes, which principally decomposed the vinyl acetate unit. An ultra-alloy capillary column UA5 was employed and helium was used as a carrier gas at a flow rate of 1 milliliter per minute. The pyrolysis products were trapped by the cryotrap until the reaction was completed, and thereafter the cryotrap was removed and the pyrolysates were analyzed by GCMS. So the pyrolysate emitting behavior of the fresh and aged EVA encapsulant samples was studied using EGA-MS. The total ion chromatograms TIC of the fresh and aged EVA encapsulant are summarized in the left figure. So two-step gas emission at approximately 350 and 450 degrees Celsius was observed from the fresh EVA encapsulant, so which corresponds to the pyrolysis of vinyl acetate and ethylene units respectively. For comparison, TG curves of the same samples are summarized in the right figure. The fresh sample also shows a clear two-step weight loss. The peak top temperatures of the total ion chromatograms slightly reduced as the UV irradiation duration increased, so particularly for the decomposition of the ethylene unit, resulting in 60 degrees for the EVA encapsulant following aging for 168 hours. The peak shape was clearly broadened by increases in the UV irradiation duration, suggesting that ethylene units having a variety of chain lengths were produced following the UV irradiation. Then the fresh and aged EVA encapsulant were pyrolyzed at 370 degrees using PYGC-MS. The resulting pyrograms are summarized here, and the summary of the peak entries and chemical structures of the pyrolysates from the PYGC-MS analysis is provided in this table. The pyrolysis of the fresh encapsulant mainly produced acetic acid, so number 7, with traces of water, this is number 5, and acetone, and number 6, and 2-oxopropyl acetate, and number 8, so which could be the product of a secondary reaction between acetic acid and acetone during pyrolysis, and aliphatic hydrocarbons are derived from the polyethylene units. So this result suggests that the selected pyrolysis temperature could mainly decompose the vinyl acetate units. The pyrograms of the aged EVA encapsulant were drastically different from those of the fresh EVA encapsulant and included acetic acid, so number 7, the carbon dioxide, number 2, water, number 5, toluene, number 9, and ketones, numbers 10 and 15, and a wide variety of lactones and anhydrides, numbers from 11 to 14. So in addition, the aged samples produced aliphatic carboxylic acids, and evidently, PYGC-MS can identify a wide variety of oxygen-containing compounds that are derived from the oxidated units in EVA. The production of ketones and lactones is consistent with the FTIR results. So furthermore, the gases evolved during UV irradiation were identified using micro-UV irradiator combined with PYGC-MS. So it is called UV PYGC-MS, so which was invented by Frontier Laboratories. So this system facilitates the UV irradiation of the samples inside the pyrolyzer at the desired temperatures and gas flow rates, and the subsequent analysis of the deteriorated samples by PYGC-MS or EGA-MS. Furthermore, it facilitates the simultaneous UV irradiation of the samples in the pyrolyzer and the in situ analysis of the gases evolved during UV irradiation using GCMS. So this work employed this system to identify the gases evolved during UV irradiation of EVA encapsulant. The EVA encapsulant was rapidly aged by the micro-UV irradiator combined pyrolyzer, and the volatiles generated during irradiation were directly analyzed by the combined GCMS. The MS chromatograms of volatiles generated during 1, 3, and 6 hours long UV irradiation runs of the encapsulant are summarized here. So the generation of water, number 5, and carbon dioxide, number 2, and acetone, number 6, and acetic acid, number 7, was observed in the early stages of UV irradiation, and the abundance of acetic acid suggests that the major component of this reaction was the degradation of the vinyl acetate unit. So in addition, the generation of aliphatic hydrocarbons was observed, and the PE unit was degraded. The number of peaks detected increased with the progress of aging, owing to the progress of complex EVA deterioration. Following 6 hours of UV irradiation, gamma-butyrolactone number 11 and succinic anhydride number 14 were identified from the EVA encapsulant. So finally, the suggested thermo-oxidative deterioration pathways by the contributions of PYGC-MS, UV PYGC-MS, and the conventional analysis are summarized here. The elemental analysis of the EVA samples prior to and following UV irradiation revealed increases in the oxygen content with the continuation of UV irradiation. The FTIR analysis verified the formation of ketone and lactone units during UV irradiation, so with ketone formation being favored over lactone formation. So these results suggest that ketone is preferably formed under UV irradiation in air. The UV PYGC-MS analysis, which identifies the volatiles evolved during UV irradiation, reveals the production of acetaldehyde and water. So these results suggested the existence of several pathways for ketone formation. So pathway 1 follows the oxidation of the methylene unit and the subsequent hydroxide cleavage, resulting in the formation of the ketone or aldehyde unit in the main chain. So additionally, UV PYGC-MS analysis identified carbon dioxide, acetaldehyde, and acetone in the early stages of UV irradiation, which suggests progress along pathways 2 and 3. The combination of thermal analysis such as TG, PYGC-MS, and EGA-MS strongly suggested the cleavage of the main chain of EVA, which may progress via oxidation as shown in pathways from 1 to 3. And pathway 4, which is known as the Norrish type 1 reaction, also produces ketones in the main chain and acyl radicals in the absence of oxygen. And furthermore, the progress along pathway 5, which is known as the Norrish type 2 reaction, was strongly suggested by the production of acetic acid during the UV irradiation. So pathway 6 may also lead to acetic acid formation. Gamma-butyrolactone was identified in the volatiles evolved during UV PYGC-MS, suggesting the progress of pathway 7, which is known as a backbiting reaction. Succinic anhydride was identified from UV PYGC-MS analysis following 6 hours of UV irradiation, which could be produced via pathway 8. This work demonstrated the usefulness of PYGC-MS and UV PYGC-MS approaches for evaluating the photo-oxidation behavior of the EVA encapsulant. Okay, so finally, let me conclude today's talk. So today I talk about analytical pyrolysis of ultraviolet deteriorated EVA. And a multi-sample micro-UV irradiator was employed for aging, multi-sample, and conventional microscopic observations. Elemental analysis and FEI analysis allowed identification of EVA deterioration. And next, UV PYGC-MS system could identify evolved gas during the accelerated aging, allowing more detailed deterioration mechanism discussion. And finally, difference of pyrolysis products distribution and gas evolution behavior between aged and non-aged EVA could be identified by PYGC-MS and EGA-MS technique respectively. So let me conclude that this work reveals the big potential of the pyrolysis technique as a way of high throughput evaluation of EVA deterioration. So that's all. Thank you for your attention.